Good afternoon, everyone. It's Friday. It's not Friday, it's Tuesday. I can't believe I thought it was Friday. Oh, God. Please, no, it's Tuesday. You know where my brain's at. I'm definitely present and focused right now. So it's not Friday, it's definitely Tuesday. So hopefully everyone's doing well. You're probably doing better than I am, clearly. So, to get started, here's what we're gonna do. In the Zoom chat, I want you to answer the following couple of questions. So I want you to tell me what you think the word work means in physics, and then I want you to tell me what you think it means to do work to an object. Right? We haven't talked about what work actually is, so I don't actually expect any correct answers, but I just want to see if anyone has any ideas of what they think work might mean. What does work mean? Anyone ideas? What is work? It does mean to function. Work does mean to function. We are functioning really hard today. Anyone else have any ideas what work means? What does it mean to do work to an object? Christina, using energy to do something. Yes, it takes a lot of energy to do work, which is true from a physics standpoint and from a life standpoint. It takes a lot of energy to do work. Takes a lot of energy to function. Anyone have any ideas what it means to do work? What does it mean to? What do you think the word work means in physics? What do you think the word work means in real life? That's also a good question. Get a few more answers in here. Got a couple answers so far. What do you think the word work means in physics? What does work mean? What do you think the word? What do you mean? What do you think it means to do work to an object? To use energy. Good. I like your thought process, Joji. That's good. It's solid. Stuff to do. Yeah. If you have a lot of work to do, you got a lot of stuff to do. Caroline, to use energy to do an activity. That's good. Actually, that is true. It does takes a lot of energy to do an activity. Do work to an object could be moving something. That's good. Monty, do something. Yes, you guys are all doing. You guys also have really good definitions for what it means to do work. When the energy does something, good. Good answer, Quinn. Emily, what energy used to move something? Good answers. So let's take another minute to see if we can get a couple more people to volunteer. We got some really good answers right now. What I think is really interesting is that work, like your definitions for work both in a real life sense and in a physics sense. And we're going to learn a little bit about the physics behind it. But I think for the most part, I think that it's very there's definitely a lot of translation between physics and the real life. So what I want you to do right now, while people are still rolling on in and answering these questions. So what I have is I have a note sheet printed out. Oh, not printed out. I have a note sheet made for you. It's on Canvas. If you go to Canvas and you go to modules, it's a red link that just says work notes. But I'm also putting it into Google in the Zoom chat so you can see it if you don't want to open it. It's just a bunch of blanks and lines for you to help you fill out some notes as you're going through it. You don't have to submit this. It's just there to help you. If you like taking your notes on paper instead, that's also fine. This is just there to help you take notes, and so you can sort of follow along the main topics that we're going to cover today. There are a couple of things that I had gone through so far that wasn't on the note sheet. So if I go through something that is important, I'll try to tell you that it's important, that you should write it down, especially if there's not a space for it. So I will try to let you know if I'm covering something important or important idea that I don't have space for you on your little note sheet. Okay, so we are going to get started with today's topic. What is today's topic? You guessed it. It is work. What? No way. We're covering work? That completely blew my mind. Yes, you're right. We are covering work, and work is super exciting because who doesn't love doing work? So let's talk a little bit about what work means. Okay. So what does it do work? What does it mean to do work? So work, in a sense, is we're using energy to do something. this is a very general term, very blanket term that sort of applies for anything, right? For real life, for physics. Work just means to use energy to do something. Now, I can make this a little bit more specific to physics. And in physics, well, usually what this means instead, what we're doing is we are using external energy and applying it to an object. Right, this idea is very important, this idea of external energy. External energy means energy that comes from somewhere else, something that doesn't happen naturally. So if something just happens naturally, it just wants to keep moving forever, then that's not external work. And we'll talk a little bit more about this for later today. But for now, I just want you to remember, okay, that work is, we use external energy and we apply it to an object. Okay.
I don't see the warm up. I can't see the board you're writing on.
That's fun. Oh, here we go. There we go. Okay, so what is work? Work is when we use energy to do something. And what it means is, more specifically, what it means is we're using external energy and we're applying it to an object. Okay, so now let's talk a little bit about what it means to do work. So when I do work to an object, when I'm doing work to an object, what it means is I'm changing an object's total energy. Right? If I'm not changing an object's total energy, I'm not doing work. When I am doing work, I am changing an object's total energy. So in a sense, you could think of this as I'm just giving energy, essentially. Giving or taking away energy. So I'm doing work, I'm changing an object's total energy, which in a sense sort of means I'm giving or taking away energy from somewhere else. Okay, so what is this measured in? How do we measure work? Well, if we're giving or taking away energy, what it really just means is that we're just measuring this in terms of energy. So the units we would use for work are joules. Just like in energy, we use joules for work. Okay, so this is more of a conceptual overview of work. What we're going to do now is we're going to take a look at more of mathematically, in terms of physics, what this work really means. So if I'm doing a work, I am changing an object's energy. So if I write this in an equation, I can say, okay, the work I'm doing is equal to delta E. Okay, so what does this delta mean? This delta symbol is a triangle. Right? You may have seen this before, you may have not. What delta means, what a triangle means, is this means change in. Right? So what I'm not multiplying this E by a triangle, because that doesn't make any sense. But what this actually means is that when I say delta E, it means change in total energy. And this is very important. This is 100% something you should remember, that delta means change in. Right? This is something you should remember because, right, if you're in the future and you're looking at an equation or you need to figure out how to solve something, and I give you a delta, right, you don't want to have to think about, I don't know what this means, because it means changing. If you know your fraternities and your sororities, you may have seen this symbol too. That's something that you'll probably know when you're in college. Okay, so that's delta. It means change in total energy. Okay, so what does this W mean? Well, W means work. So in other words, if I apply some amount of work, some amount of W in, I change the total energy of my object. Okay, so what is total energy again? Well, total energy sort of means our potential energy plus our kinetic energy. So if I'm changing my total energy, I can do this by changing either my potential energy, I can do this either by changing my potential energy, or I can do this by changing my kinetic energy. So if I change either my potential energy or I change my kinetic energy, I am essentially doing work to an object because I'm changing my total energy. All right, so remember here, we got a couple of delta symbols again. So delta P, what does delta P mean? Delta P means change in potential energy. What does delta K mean? Delta K means change in kinetic energy. Okay. So, in other words, right, the work I apply is equal to the change in energy, and the change in energy is equal to the change in potential energy plus the change in kinetic energy. So I can also just say, hey, the work I apply is just equal to the change in potential energy plus the change in kinetic energy, right? Each one of these is equal to each other. My change in total energy is just equal to my change in potential energy plus my change in kinetic energy, which is also just equal to the work I apply. Okay, so let's see what happens when we start doing a little bit of work. So if I apply a work of 100 joules to an object, what it means is I am changing the object's energy by positive 100 joules. I'm increasing the object's energy by 100 joules, the total energy by 100 joules. What if I apply a work of a negative 100 joules? Well, this means that our total energy changes by negative 100 joules. This means that, okay, that our work can be negative. And when my work is negative, I'm decreasing my total energy. When my work is positive, I'm increasing my total energy. Okay, so now let's see exactly how this works. So what I want you to try, we'll see how we can do this. So we're just try with a little practice problem, and I'll do it on the board afterwards. And I want you to see if you can use what we've learned so far and see if you can at least figure out how to start. So in problem number 1, I have a dumbbell that is 20 kilos, no, 100 kilos. And so I lifted it 2 meters above the ground. So I want you to tell me how much work did I do? This is not okay. So I haven't really told you a lot about how to figure stuff out with this yet, but I want you to see if you can at least try, at least think about what we can do here. So I'll give you a couple minutes to try this out. Then what I'll do is I'll start trying to walk us through this. So I think the best way to start here is when we look at work, we want to look at the change in our energy, right? And when we look at our change in energy, we want to look at, okay, how is my potential energy changing? How is my kinetic energy changing? So I think the first thing we want to do here is we just want to figure out, okay, what is our initial potential energy? What is our initial kinetic energy? So I've written this down on the board. What I've written down here is PI. So PI means initial potential. This does not mean P multiplied by I. this I is like a little label for a potential. It's like a little sticker on your car. So this I is a little sticker for this potential, and same with this kinetic. So everyone on the chart here, okay, what is our initial potential energy and what is our initial kinetic energy? So remember that our dumbbell starts on the ground. So initial height is 0 and initially starts at rest. So can anyone tell me what my initial potential energy is and what my initial kinetic energy is? The dumbbell starts initially from the ground. Any ideas? What is my initial potential energy? What is my initial kinetic energy if my dumbbell, my barbell is starting from the ground? Okay, so we've got a lot of good ideas so far. It seems that we've reached the consensus that my initial potential energy is 0. You're like, Mr. Hill, how do you know that? Well, if the barbell starts initially from the ground, it has a height of 0. So anytime something starts from the ground, it has 0 potential energy. Okay, so okay, potential energy is a little easier. What about kinetic energy? Well, if the kinetic energy relates to the movement of the barbell, if it is initially on the ground, it's not going to be moving, right? The barbell doesn't move on its own. So it also has 0 initial kinetic energy. Okay. So now let's take a look and see, let's see if we can find our final potential energy and our final kinetic energy. And remember, when I lift the barbell to the top, right, I'm holding it at the top. So it's not moving at the top anymore. I'm just holding it. Let's see if we can figure out our final kinetic energy. Figure out our final potential energy. I'm holding at the top. What is my final kinetic energy? What is my final potential energy? Anyone have any ideas? What our final potential energy is when we lift it at the top? What our final kinetic energy is? Okay, so let's take a look at figure our final potential energy first. Final potential energy is our mass times gravity times height. Our mass is 100, gravity is 10, height is 2. This ends up being 2,000. So we found our final potential energy just by looking at the mass of the barbell, the height of it, and the gravity. Anyone know what the final kinetic energy is, right? When I hold my barbell at the top, right, I'm not moving it anymore. It stops moving at the top. Anyone know what the final kinetic energy is? Final KF. Final KF is indeed 0. When I hold it at the top, right, I lift it to the top, it stops moving. Okay, so now let's take a look at finding our work. Okay, so our work is our change in potential energy plus our change in kinetic energy. Okay, well, it looks like my kinetic energy didn't really change. If I start at 0 and end at 0, my kinetic energy changed to 0. This just goes to 0. So let's look at how our potential energy changes. Well, the change in our potential energy, we could say is, okay, this is our final potential energy minus our initial potential energy. So what does this mean? amount of work I apply is equal to the change in potential energy plus the change in kinetic energy. We know that the change in kinetic energy is 0 because it starts off at 0, ends up at 0. My change in potential energy is my final potential energy minus my initial potential energy. And that tells us how much our potential energy changed. So what I wrote down here is I wrote down my final potential energy minus my initial potential energy. And this gives us our delta P, or change in potential energy. We know that our initial potential energy is 0 because it was on the ground. And so we just get that our work redone was 2,000 joules. So let's see if I can, maybe explain this delta P a little bit more. So delta P, right, again means our change in potential energy. So you could say that, okay, this is equal to our final potential energy minus my initial potential energy. So if I were to break this down a little bit more, I'm going to simplify it a little bit more, right? When I'm changing an object's potential energy, all I am doing is I am lifting it up or down. I'm not changing the mass, I'm not changing gravity. All I'm doing is I'm changing the height. So so this is your general equation, right? Final potential energy minus initial potential energy. I could simplify this a little bit more if I really wanted to. It's just mass times gravity times my delta H. But delta H means change in height. And this is if you just want to make things a little bit simpler, figure out how our potential energy changes, if you know how much your height changes. Are we good so far? Does anyone have any questions about the deltas, the subscripts? Okay, yes, no, okay. So what I'm gonna do is I'm gonna erase this problem. Hopefully you have it recorded. I'm gonna go to the next problem. The next problem is I have a car or object, and I am applying 1,500 joules of work to it. The car is initially at rest. It's on the ground. And I want you to figure out what is my final kinetic energy and then my final velocity. So I think the best way to do this is let's look at let's first set this up. Our work is equal to the change in kinetic energy plus my change in potential energy. So what I first want you to do is I want you to tell me what is our change in potential energy and what is our work. That'll get us a start. So for this problem, what I have is I have an object. The object I think has what was the mass of the object? It was a 30 kilogram object. So this is a 30 kilogram car. I'm applying a work of 1,500 joules of it. The car is initially at rest. It is on the ground. And I want you to tell me what my work is. So what is my work? The work I apply to it. And I want you to tell me what my change in potential energy is. Anyone have any ideas? So what's 1,500 joules? Which one is that? Is that my change in potential energy? My change in kinetic energy? Change in my work? What is that? Right. So the work I applied is just 1,500. As we said so in the problem. Okay, what about delta P? Well, if I am neither going up or down, because all I'm doing is I'm pushing the car right. So I'm going either up or down. I'm not changing my potential energy at all because the height is not changing. So I'm not changing my potential energy at all. This just becomes 0. So now I know that my change in kinetic energy is equal to 1500 joules. So can someone tell me what my initial kinetic energy was? $1,500 is equal to the change in kinetic energy. The change in kinetic energy is also equal to the final kinetic energy minus the initial kinetic energy. Someone know how much our initial kinetic energy was? How much kinetic energy did the car have? Well, if the car was initially at rest, it means that it was not moving, which means that our initial kinetic energy was also just 0. So that means our final kinetic energy was just 1500 joules. Okay, so does someone want to help me figure out what the final velocity is? What's our final velocity? Okay, so to figure out our final velocity, what we're going to do is we're going to take our kinetic energy, set it to 1/2 mv squared. So this is the equation for kinetic energy that we're going to use to figure out our velocity. Our initial kinetic energy at this point is 1500. It's equal to 1/2. Our mass is 30, and then we don't know what v squared is. 1/2 times 30 is 15. So 1500 divided by 15 is the v squared. 1500 by 15 is just 100. So 100 is equal to v squared. I'm not done, because I need to get rid of the v squared. I just want to figure out what v is. So to do this, we use the square root function. And get that v is 10 meters per second. Okay. Does anyone have any questions about how I did this or the previous problem? Okay, so while writing this down, I'm just going to erase the top section here. Okay, so let's talk a little bit about what it means to actually do work on an object. So I just told you, okay, we can just do work to an object. I can just give it more energy. But I haven't really told you what it means to actually do work on an object. Well, to do work on an object, we need to apply a force over a distance. So what is a force? Well, a force literally just means a push or a pull, right? If I push or pull an object, I'm applying some sort of force. And when I apply this force over a certain amount of distance, I will do work. I will change the object's energy. So what is force? Well, force, again, is a push or a pull. And we can measure this using the unit Newton, named after Sir Isaac Newton, or the Fig Newton. And we usually signify Newton with just the capital N. Very important to remember. If you see what N is just a force. So to do work, I apply a force over a distance. So let's see if we can write this down in terms of an equation. So work is our change in energy. Work is also equal to the force I apply multiplied by the distance. So if I want to do work on an object, I apply force over a certain amount of distance, and this will change the object's energy by some amount. So to do a quick practice problem, I have a book on a table. I apply a force of 1 Newton, and I move the book 2 meters. So I just want you to figure out how much work did I do to do this. I apply a force on a book that is initially at rest, and I move the book 2 meters. How much work did I do? Takes a force of 1 Newton to push a book 2 meters across the tabletop. How much work was done in moving the book? So to do this, okay, the work I do is equal to the force I apply times the distance. So I apply a force of 1 Newton. I move the book over a period of 2 meters. So I get my unit. So I get my work is equal to 2 joules. I remember that work is measured in joules, just like in energy. Okay, so the second part of this problem is more complex. And what it says is, okay, the book is initially at rest, and the book ends up at rest. So even though we gave this book kinetic energy to make a move, somehow it lost all of its kinetic energy again. So where did this energy go? Why, like if we did work on it, why does the book still have no kinetic energy at the end? Okay, so this is where we need to identify that even though we did work on the object, there is still another source of work being done. So what we have done is we have given the object positive work because we've sped it up and we've given it some velocity. However, when you slide a book around a table in real life, it will slow down, which means that there has to be a source of negative work. There has to be something, some force that is applying a negative work to it to reduce the kinetic energy, to do negative work on it until it reaches 0. Okay, so what actually slows down the book and stops it when you move it across the table? When you slide a book across the table, it's creating friction between the table and the book. And this friction creates thermal energy from the kinetic energy of the book. So this force of friction, this friction force, is slowing down the book by doing negative work on the book and reducing the amount of kinetic energy it has. And because this force of friction is doing negative work, is slowing it down, you can, in essence, think of it as being a negative force, a force that is doing negative work. It is slowing down an object. Okay, so there's one other thing that is important. So one thing I've talked about before was how work needs to be done through an external source of energy. Now, naturally, one might think, okay, when I drop an object, right, it's moving, therefore work is being done. However, that is not true because gravity does not do work on an object. Gravity, we don't consider gravity to be an external force because when you drop an object, it falls naturally. So it's not really an external force that's acting on it. It's just something that just happens naturally. And additionally, gravity doesn't change the total energy of an object. It does not. When something falls, gravity does not give it extra energy. All what gravity does is it converts kinetic energy into potential energy into kinetic energy. And when the object is going up, right, gravity is converting that kinetic energy into potential energy. So gravity itself is not doing any additional work to an object. All what it's doing is changing how the distribution of kinetic and potential energies are. So one time it might have more kinetic energy, one time it might have more potential energy, and all what gravity is doing is it changes that around. It changes what has more, it changes what has less. It does not change the actual total energy of the object. This is very important because work is a change in total energy. It's not necessarily a change in how the energies are distributed. It's just a change in whether or not the object is doing work. And so this is where we sort of tie in our conservation of energy, right? Energy is always conserved. And if their energy is not being conserved, it means that there had to have been some sort of external work, some sort of external energy being applied in order to give the object more energy than initially started off with. So that's a very important concept as well. What work actually means. It means you're changing the total energy of an object. Okay, so there's one other problem here, another practice problem, and it's just an object that is falling. So if an object is falling, a 10 kilogram object is falling from a height, how much work is being done? If an object is falling, how much work is being done? Object is falling, how much work is being done? Does it even? This is a very long and complex problem, but actually the work is just 0. There is no work being done here. All that's being done is gravity is just changing the potential energy into kinetic energy. There's no work being done. Okay, so I want to give people a chance to ask any questions. Does anyone have any questions? Does anyone have any number on the note sheet that they didn't get? Anything they want me to explain more of? 18, okay. So for 18, gravity does not, with a big caps lock, bold, underline, gravity does not do work on an object. This is because we do not consider gravity to be an external force, as it does not change the total energy of the object, only how the kinetic and potential energies are distributed. That's for number 18. Does anyone else have any questions? Anything they want me to go over? Okay, so if you don't have any other questions, you can always ask. Oh, 14. Okay, 14. So for 14, force is the force applied to an object, which is measured in N, shorthand for newtons. So force is the force applied to an object. That's seems kind of redundant, but force is the force applied to an object, which is measured in N, which is just shorthand for newtons. Anyone else have any questions before we move on? Okay, we don't have any questions. So here's what's going to happen. So I'm first going to talk a little bit about due dates. I've got to do that at the beginning of class. So quarter grades are due the 9th. I want to have all the assignments turned in, hopefully by the 7th, so I can have time to grade them for the 9th. If you turn them in a little later than that, I cannot guarantee that I'll have them graded in time. So which means that you need to have parts 3 and 4 completed and submitted hopefully by tomorrow. Parts 3 and parts 4. Those are mandatory. If you don't complete them, I will have to put a 0 for you in the grade book until after you complete it. This doesn't mean you will receive a permanent 0, but for your quarter grade, you will receive a 0 for those assignments if you don't turn in 3 and 4. 5 and 6 are optional. So if you don't turn them in, you won't get a 0 ever. However, if you want to have that reflected in your grade for the quarter grade, you should turn it in by the 7th as well. Now for any assignment, you can turn them in after the 9th, after the quarter grades are due, and I will still grade them with no penalty. But because those are submitted after the date, I just won't be able to put them in your quarter grade. So it really just depends on, do you want a good quarter grade or not? So that's for that.
I have a question about that. So is this stuff the work, like the work proficiency worksheet and like the work mastery worksheet? That's not going into our quarter grade, right?
No, yeah, correct. It is not going into your quarter grade. That we will pick, because we will pick that up on Friday. So you don't do that for homework at all. Just instead focus on doing 3 and 4 as well.
Okay.
So yeah. Do you need to get a perfect score in the mastery parts to get to get an A? So to get an A, you need to be, in general, you need to be earning 4s on your masteries. So I think right now, because we have 3 standards, you need to be earning something like you need to be earning at least 2 4s out of 3 standards to get an A. So you do need to get a perfect score on at least one of the mastery assignments to get an A. Yeah, but you can always resubmit those if you don't. But I think it's more important just to focus on, do you really demonstrating that you've understood the content fully. So that's what the criteria is for grading. Okay, so the next thing I want to do is now we are going to start the work proficiency assignment. It's on Canvas. It's titled Work Proficiency. That is the assignment we'll be working on for the rest of today. If you don't finish it, no one's going to finish it today in class. If you don't finish it, you don't have to do it for homework. We'll pick it up on Friday. But I want you to start on it and get as far as you can and ask me any questions you may have. And let's see if you can, get at least a few questions down. If you haven't turned in parts 3 or 4, I would maybe instead work on that instead today. If anyone else doesn't have any questions, I'll let you get started. And if you have any questions, just let me know. Oh, and I'll be going around and seeing where people are in terms of turning in stuff to make sure that everyone is on top of things. So word proficiency assignment, that's what we're doing right now. So we have a minute left, so I'm just gonna wrap up. Well, we're out of time now. So just finish part 3 and part 4 by tomorrow, and I'll have start grading those by Friday. You can take more time if you need them, but just try to submit as much as you can. Otherwise, you're free to go. I didn't get a chance to answer everyone's questions if you've had any. So if you have any questions about work, if you have any questions about part 3, part 4, you can ask me right now. That's okay. Or come to office hours, which is 2:40, 3:40. Otherwise, you're free to go. And I will see you all on Friday.
Thank you.
Thank you.
You.
Thank you.
Mr. Who?
Yes.
So I submitted, I think it was part 4. I resubmitted it, but it still has the same grade and it has the same like corrections. Does that just mean you haven't gotten to it yet, or is there something else I need to
Part
correct?
4, I think I graded your part 4. So with part 4, let's see. Hold on. I might have looked at it. Okay, so the last submission I got from you was September 25th. So I don't know if you made any changes since then.
I remember staying in one of your office hours correcting I think it was number 3, and that's still like the corrections of like what I need to correct or whatever, you know?
So you did number 3 correct. It's just that you messed up your velocity calculus. I think that was the only thing you messed up on.
Yeah, and that's what I stayed in to correct, I think. I think I had different measurements in, and so I stayed in during one of your office hours and I corrected that, so.
Okay. So yeah, I if you just put like, honestly, if you just put in like a comment with the number you got, or if you just put it in the document, I'll update it. Because when I'm just looking through this, I'm not like necessarily remembering what you got for it.
Okay, so I'll just put like a comment in the grade book, I guess?
Yeah, just put a comment on the submission, or you can just resubmit it. Whatever one works.
Okay.
Yeah, because I guess when I'm grading it, like I won't necessarily remember stuff like that off the top of my head. So it's easier for me if I just see it in front of me.
Okay, thank you. I was just wondering if you just.
Yeah.
Whatever.
Okay.
Thank you.
Okay, perfect.
Hi, I just have a clarification question. So I did the